Hello and welcome to aTech. Today we're exploring Optimus, the Tesla humanoid robot, from its origins to the concrete advances of 2025 within the context of a global race toward physical automation. How does Tesla plan to operate a bipedal robot using the same artificial intelligence that drives its cars? In a market dominated by specialized machines, why is Optimus betting on low cost and mass production? And finally, beyond the promises, what are the concrete implications for employment in the global economy of this new generation of humanoids? The answers in this video. The story of Optimus was not born on a traditional robotics laboratory, but at the heart of Tesla's automotive ambition. In August 2021, during its AI Day, Elon Musk presented it as a logical transposition of technologies developed for autopilot. The founding idea is simple. If a vehicle can navigate the real world, interpret signals, anticipate movements, and make decisions solely based on its computer vision and neural networks, why couldn't intelligence be housed in a bipedal body to perform physical tasks? The robot's architecture, therefore, rests on this so-called end-to-end AI, capable of linking raw sensory data, captured by cameras identical to those in cars, to immediate motor actions. Learning, which is fundamental, operates through human imitation and reinforcement, capitalizing on the millions of hours of data accumulated by Tesla fleet. The first prototypes unveiled in 2022 and 2023 were cautious proof of concepts, demonstrating still hesitant walking, the carrying of light objects, and the execution of basic gestures. But these initial demonstrations, despite their rudimentary nature, laid the foundation for a vast ambition, that of progressively generalizing automation to all spheres of human work. It was the starting point of an aggressive roadmap. The year 2025 marks a break from the era of clumsy prototypes to enter the phase of measurable iterations, symbolized by the Generation 2 Optimus. This Gen 2 version shows tangible progress that brings it closer to industrial utility. Its weight has been reduced by about 10 kilograms, which significantly improves its energy efficiency and agility. As a consequence, its walking speed has been increased by 30%, allowing for smoother and faster movements on production lines. The Optimus 2 now boasts a nominal load capacity of 20 kilograms, making it capable of handling the majority of manufacturing parts and tools. The improvements are not only motor-related, they're sensory. An articulated neck, integrating advanced sensors, allows for a mobile and more responsive head, improving spatial orientation and risk perception. Refinement also focuses on fine manipulation, the arms are more precise, and the hands integrate an increased number of degrees of freedom, allowing for the sorting and movement of delicate or complexly shaped objects. Tests are multiplying in controlled environments, particularly with Tesla factories. These trials validate better balance management, including after disturbances, and extended energy autonomy, allowing the robot to operate for several hours. Pilot lines mobilizing these second-generation units are beginning to activate, confirming an internal deployment by the end of 2025, where Optimus handles fragile parts on assembly lines, surpassing in certain repetitive tasks the consistency and endurance of new human operators. But Tesla's horizon extends beyond the Gen 2. The real leap toward manufacturing utopia is planned with the Gen 3, expected in the first quarter of 2026. This generation aims for a design 70% closer to the human body, with integrated cabling and actuators for more natural, almost human-like movements. The software ambition is exponential. The Gen 3 is expected to master 1,500 initial tasks, a repertoire that could be extended to 3,000 via simple over-the-air software updates. The hands would continue to gain dexterity, and the robot could integrate a facial OLED screen, as well as the conversational intelligence of the Grok model for smooth human interaction. The roadmap doesn't stop there. The Gen 4, projected for 2027, is designed to perform up to 5,000 tasks with a level of precision already described as superior to humans, particularly for delicate operations or fatigue-free repetition, such as surgical precision. Behind these figures lies Elon Musk's economic vision. He anticipates mass production of Optimus exceeding the annual volume of smartphones to catalyze an economic abundance where hard or repetitive physical labor would become an option, no longer a human necessity. In this global race for physical automation, Optimus is far from alone. It operates in a competitive arena where players with very different philosophies compete. The Tesla robot competes with sophisticated machines like Figure AI, designed in partnership with BMW and focused on warehouse operations, or Agility Robotics Digit, already tested in logistics. Not to mention pioneers like Boston Dynamics Atlas, famous for its spectacular agility, or Unitree's agile and affordable machines. However, Optimus stands out for its unique strategy, where competitors often focus on cutting-edge agility or dexterity at a high cost. Tesla prioritizes mass production and a low target cost, announcing a potential price of $20,000, a fraction of the cost of current specialized models. This approach targets in-factory reliability and unprecedented scalability, directly linked to the autopilot software ecosystem and the dojo training infrastructure. While players like NVIDIA are accelerating the collective maturity of robotics simulation and training platforms, real-time adaptation to unstructured environments remains a technical limitation shared by all players of the sector. This forces each to make strategic compromises between niche performance and low-cost generalism. Despite the measured progress in 2025, the road to widespread adoption is fraught with obstacles. The massive and independent deployment of Optimus in unforeseen environments has not yet been verified. Autonomy in uncontrolled situations remains low, and handling unexpected events is limited, still requiring significant reliance on prototype environments. On the technical front, obstacles persist. Energy autonomy for full work shifts, mechanical robustness for intensive use, and cybersecurity, especially emergency stop protocols and human intervention, still require continuous refinement. Financial analysts, such as those at Bank of America, have noted the execution risks associated with overly ambitious timelines for Optimus and the robotaxi, sometimes adjusting Tesla's rating to neutral. These technical challenges are compounded by profound societal and ethical issues. Optimus inevitably raises the question of employment. If it's designed to take over arduous tasks, it also risks accelerating massive restructuring. Physical safety, ensuring non-dangerous force limits, and proximity detection to operate alongside humans impose emerging standards, while social acceptability and the need for international regulations will have to govern its use in hospitals, homes, or commerce. Optimus thus embodies the transition from niche robotics to the versatile humanoid, tested in the crucible of Tesla's factory before industrial expansion. It reflects a future where economic choices, mass automation, or protected niches will shape the coexistence between man and machine. That concludes this analysis. Thank you for following along to the end. If you enjoyed the video, feel free to leave a like and tell us in the comments your opinion on the future of robotics and Tesla in this field. New episodes are coming soon, so don't forget to subscribe to the channel and hit the bell to stay updated. I'll see you very soon.